I need to start by telling you a little bit about my programming stuff. I only do Fortran. Okay, and I do not do CUDA Fortran. I don't do CUDA, I don't do C, I don't do C++, I do Fortran. Okay.
I bet you can't even spell C.
Okay, the other thing, I mean, there's a lot of talk this morning about kernels. Doug Miles and I have had this discussion a long time. Kernels are for people who are used to programming in CUDA and want this converted to CUDA. Parallel loop is for those of us who are familiar with OpenMP and basically say, I know this loop is parallel, this is the way I want you to generate code. And so all of my examples use parallel loop. I don't use kernels. So we have a significant challenge. And the challenge, I believe, is more difficult in the oil and gas industry. The problem in the oil and gas industry is that there is a lot of data to be moved compared to the amount of computation that you perform. Now that is getting better with higher order computation. But, you know, the bottom line is that this is an XC30 Haswell system with a K40 attached. And the real minimal transfer rate here is that PCI Express bus. If you notice, you have 200 gigabytes per second on the K40. You have 64 gigabytes per second on the Haswell. The length between the K40 and the Haswell is only 8 gigabytes per second. And then off the node is 8 gigabytes per second. So really, what you're looking at here is you have a significant computational resource on that accelerator. But the bandwidth over there is less than what you would like. The other problem is the amount of memory over there is less than what you would like. Now, in Cray, we have a lot of procurements where people submit a suite of applications saying, okay, show us the best you can do. And, you know, the options are that versus this, which is a 2-socket Haswell system with a lot more bandwidth between the 2 sockets. And so there's a tremendous challenge here to utilize this to outperform that. Now, NVIDIA is definitely improving the accelerator. There are other accelerators coming down the road. But the bottom line is that even though this thing uses more power, this is the node that you have to outperform. Okay, so the thing that we really need to do is to basically optimize the computation on the accelerator. So this is one of the first things. Now, people were talking about computational intensity earlier today. The bottom line is the accelerator has more memory bandwidth than the host. So even if you have low computational intensity, it certainly is the fact that the performance on the accelerator can be better than on the host, especially for gather-scatter. Gather scatter is something that needs a lot of bandwidth. And as we see here, the bandwidth on the accelerator is more than the bandwidth by a factor of 3 than the bandwidth on the host. So, we really want to do computation and significant data motion on the accelerator. The next thing, though, is because the seismic processing not only has to bring in a lot of data, manipulate that data, output something, and do imaging, you have a tremendous amount of data motion moving around the system. And when you use the accelerator, you're introducing another level of data motion that you didn't have without the accelerator. So all this really means that you have to pay very careful attention to overlapping. The previous speaker talked about overlapping computation and data motion. Actually, if you think about it, on the accelerated system, you have 4 levels of parallelism. You have MPI, you have threading on the node, you have vectorization, but NVIDIA is not a vector machine, it's a SIMD, it's like the ILIAC 4. Does anyone know what the ILIAC 4 is? Yes! Okay. But anyways, because it really is a parallel SIMD parallelism within a warp. And then you have streaming. Streaming is an added level of parallelism that very, very few people utilize. And I think you have to utilize it in order to really get the best performance. So, now I can't show you oil and gas benchmark or kernel or anything like that. So I'm going to use Hamino. Have many of you played with Hamino? It's an awesome toy because it really illustrates a significant number of the issues that you have to address. It's very simple. There's only one important kernel. When I look at a code that I want to put on the accelerator, the very first thing I do is convert it to OpenMP. And then I put on OpenACC. So I want to kind of step through this. Now, I have to say, now I am a little biased because I work for Cray, but Cray has the best profiling tools in the industry. And so the very first thing we do is we look at this profile and we see that there's one kernel that's using 94% of the time. But a really cool thing with our profiler, we can also get the loop iteration count, the average, min, and max. And so we really can see how the loops are nested. We know the iteration count. So we can really start getting a good feel of how we might map it onto a multiprocessor. All right. The other thing is Duncan mentioned that, so we did this whole program analysis a long time ago. But it was only good for Fortran 77, but it really did use a database representation. And the cool thing is it could do scoping of loops that called subroutines and functions. And it turns out that I'm teaching Cray how to do this. And so we have this thing called reveal. that actually does scoping, and so reveal automatically parallelize this loop. It doesn't call subroutine or function, but it deals with that as well as the other. Then, you compile the reveal output. You see that this loop is done multi-threaded, and the inner loop is vectorized and unrolled by 3. So we have a nice open MP code, not optimal because we only did one loop, but we can now introduce OpenACC. So we have an if-def OpenACC, this, else do the OpenMP. And here again, it's just the kernel. So like Ty's presentation, we're just looking at that one kernel. The reason I like this is a stencil. So a really important computational kernel in the oil and gas industry is a stencil. And so you have similar, you're also doing a reduction function inside that loop. And now the Cray compiler takes this. This is the accelerated region, and then you have, it only parallelized 2 of the 3 loops. But the cool thing then is it tells us, if you're going to put that on the accelerator, all these arrays have to be copied over and other arrays back. And now I do a profile of that execution, and I see the data motion is using 85% of the time. Very, very similar to time. So then the next step is so we've identified a kernel, we put it on the accelerator, now we have to get rid of all that data motion. This is the hardest part. And that is, we want to introduce a data region outside the time step loop. We want to move data over to the accelerator before we enter our time integration. Now, if we do that, then all of a sudden, we have to manage 2 copies of the data. The host has a copy, and the accelerator has a copy. And this is the difference from easy and difficult. This is hard. Okay? Because one of the main reasons is there's not a tool that says, inside this data region, show me all the places where this array that I want to put on the accelerator is touched. Okay, that would be awesome. So, I do that analysis on this code. Now when I come into this routine that has this major kernel, all of these arrays are present. In this, I'm going to create it if it isn't present, create it on the accelerator. So this kernel is pretty much the same, but now I have to deal with this. Because after this kernel, then I copy it into the P array. This innocent little SynP is doing halo exchanges. Now, think about this. Should I transfer the entire P array to the host and have SynP work on that array and then send the entire P array back? All right? So I'm going to try that first. And anyway, so I do that, and the time went from 64 seconds to 32. So I got a factor of 2. by having the data reaching out, but still 66% of the time is spent doing these two transfers. Okay? You should never, ever, ever use derived types when you're doing MPI on accelerated arrays. Because derived types are packing the buffers on the host. So what you have to do is you have to pack the buffers. You have to pack those halos to send to your neighbors. And that is very nasty. Okay. So the problem is I have 6 neighbors. Okay, and I have to exchange a halo with each of my neighbors. And so I have to pack up all of these buffers. I then update the host with those buffers. And then I basically have to unpack. This is nasty. It's worse if you have irregular grids. This is without a doubt one of the most difficult parts of using the accelerator. And so now, basically, this is in fact the performance I'm getting with that last rewrite. So we basically, this is the original that was running on 16 nodes, 4 MPI tasks per node. And then now we come down, so we get about a factor of 7 or 8. But that's not all. So there are 2 things that we haven't done. What we've been doing is, Ricky Kendall always said, whack-a-mole. So whatever's using the most time, you basically want to address that. So we've just addressed the memory transfer issue between the host and the GPU. Now, one thing that we didn't do yet is we have not looked at the kernel performance because the kernel was running so fast compared to the data motion. So this is another very difficult issue in OpenACC. And the reason it's a big issue is because the compiler compiles your code before runtime. The compiler has no idea what the sizes of those loops are. All right, now there are directives where you can give the compiler hints, but the bottom line is that you really have to design your directives according to the size of your problem. And so this is, in fact, Alistair Hart, who is apprentice wizard in the UK. I actually did a study of Hamino with 4 different problem sizes. And in these, he actually was playing around with the vector length. So the length that you want to divide that vector loop on. And as you can see, with the 4 different problem sizes, a lot depends on the problem size. Now, his solution was at compile time, you could define your vector length and pass that to the compiler. But that's, not really the best. Now, there are other ways of dealing. In fact, why don't I go to this? this was the initial naive approach that the compiler took. And they're really, on the accelerator, you have the ability to do 3 levels of parallelism. You have gangs, you have workers within the gang, and then you have vector, which is the number of threads that are going to be SIMD or SIMD. So basically all this is doing is a gang of vectors. Now I can convince it to basically employ worker as well. So I have gang, worker, and vector. But one thing that works extremely well is collapse. So here, in a multi-nested situation, you can collapse loops together. In this case, we're collapsing these 3 loops together. And then, at runtime, the compiler can decide how to break things up. Okay, so this is really very good. And you see that introducing the worker level actually slowed it down a little, but using collapse actually got a nice improvement. So if I go back to Alistair's, and so he basically was collapsing 2 and 3 loops. And here again, it is problem dependent. But I think the green, I think is typically, except for a very large case, green kind of worked pretty good. Okay. So this is another one of Alistair's slides, and so he has a really good presentation that is on. Do you still have the slides up from that OpenACC? I think you do. So on Oakridge, if you look at workshops, there was a workshop we gave in 2013 that has a lot of really good slides on OpenACC.
It's on GitHub.
GitHub. Okay, now let's talk about async. I can tell you with S3D, there's no way we are going to get acceptance of Titan without async. And basically what async does, it allows you to submit a kernel, a parallel loop, to the accelerator, and the host gets control back. So it's like an asynchronous message. And you can have up to 16 of these, we call them streams. And now, I actually had 30 streams in S3D, but all they do is, they do a mod, and so stream 17 waited for 1. So, and then you could wait for a specific stream or all the streams. All right. So this really enabled you to get another level of parallelism. Now, Alistair has a simple example where basically he's doing an async on this J loop. Now, this is really kind of interesting. I've been working with a fella at the Danish Met Office, Jacob Wiseman, and he uses OpenMP like no one I've ever seen. Basically what he does is he has a large parallel region, and then he calls a routine that does its own load balancing and gives the each thread the bounds of the grid to work on. And so he said, put OpenACC into this. And so what I did is I actually used his thread number as async. Because then down within he has all the parallel do's where the threads were now dividing the work. So this async can really be used very nicely for handling OpenMP structures that do that kind of thing. This is basically the CPU, the OpenACC, where you're actually not using async and then using async on that very simple problem. And so this is really showing you how the various, so red is the data transfer, pink is computation, this is over and back. So you can see how the overlap of these 16 threads is happening here. So this really is a simple example, but in fact it works extremely well on very large codes like S3D and other stuff. Now, another thing we want to do is we really want to optimize the data movement from the GPU out to the interconnect to another node GPU. There is a very, very nice thing in OpenACC where you have a host data region and you basically say use device F. So these Fs being passed down into these ISINs is coming from the GPU. It's not going through the host. Now, it turns out on our system, the MPI library looks at the size of the message. If these messages are small, the length, then it does go directly to the interconnect without going through host memory. If that message is larger, it actually has found out that pipelining the transfer on the host is faster than sending it directly to the interconnect. So using this will get you the best performance. However, it might not be true GPU direct. And now this is the other thing where you could easily use a CUDA library call, that kind of thing. Now this is something I love working at Oakridge. So they have some very challenging users. And Jack mentioned this group in Denmark that's working on DL Dalton? LS Dalton. Now what they're actually doing is using MPI-3 one-sided message passing with this. So the cool thing about that is that you just send it off to the other host, and this guy doesn't have to worry about that message anymore. So he's getting really good performance with one-sided message passing. Now on the receiving end, if you're doing these ISINs, so we typically run large core or node counts, like 15,000. And if you're on a 3D torus, like Titan, your messages are not going to come in order. And so when you're doing this, you really want to pay attention that as you receive the message, that you want to wait on any message, not a specific message. And then, depending upon which message it is, you then update the device. And this is all using async. So the bottom line here is what you're doing is you receive any message, you update the device, and wait for the next message because you get control back immediately. Because all these updates go on in parallel. Okay. I have 15 steps because this is not easy. I mean, when you're working on real applications, it's very hard. And you have to buy a Cray so you can get excellent application support. Just kidding. But anyways, first and foremost, you have to profile the application. You need to do high-level parallelization. And then we let the compiler find out what arrays need to be transferred. And now this is the hard part. So once you do the highest level loop, you then have to worry about data. Look at the next one and make sure that the data is where it should be. And then you combine multiple loops together. And pretty soon you're outside of the time step loop. And this is very important. This is something I never pay attention to. I always do multiple steps at the same time, and then I get a bug. And then I take all weekend to try to find it. Then when you're at the end, so a cool thing is you generate these listing files from the compiler, and I always do a grep on copy. And because then all of these, because the compiler may introduce some data motion that I didn't expect. Okay, and then you optimize the data. And then if the bottleneck is kernel performance, then you want to look at that. You want to consider CUDA streams, and you have to do this. So Intel has showed this is basically a timeline showing you CUDA streams, different CUDA streams. The problem with the CUDA stuff is that it typically is only for one MPI pass, but I think Jeff has something that...
Yeah, Vampire can do some with the GPU.
Vampire is so hard to use.
No doubt.
Okay. Oh, and I can't... Okay. Vectorization is a lost art. Okay, there are very few people in this room that know how to vectorize code. Now, and then there's good and bad vectorization. This vectorizes. This is a piece of junk. Don't ever use array syntax. Michael, is array syntax good for you optimizing? Don't say yes. Don't say yes.
It's never better.
Okay. So anyway, all the mesh loops are in these array assignments. This was one of the main routines in S3D. It vectorized, but it ran very slow. This runs extremely fast. Okay, we unrolled the loop on direction, and there's no array syntax in this. Vectorization is extremely important going forward on every, even on Haswell, Broadwell, etc. Now, before closing, I want to mention a couple things. There was a totally awesome development at CSCS in putting Cosmo on accelerators. This was actually funded by CSCS. They spent, I think they invested like $2 million in porting this to accelerators. And it took a year and a half. And this was kind of their first, decision. And that's a nice thing. I want you to find a bold and innovative way to do everything exactly the same way it's been done for the 45 years. That's me. Okay, so basically, the stencil computation in the dynamical core was done with a DSL. So this was down at the bottom, it's all very highly optimized CUDA. And it's very highly optimized packing and unpacking of buffers. And it's basically a DSL that can be employed in any code. Now, they have offered this code to people. This will do any kind of stencil operation, and it's highly optimized. The rest of the code, which is about 350,000 lines of Fortran, is done with OpenACC. Now, the cool thing, this was back in November 2011 on an XE6. So from there, they got a factor of 3.36 performance. But the cool thing is they got a factor of 7 in power savings. This code runs every day. In 1 year, they more than paid for that $2 million code conversion. So this is your new ploy here. You write your proposals to hire some really smart optimization people. And you say, look, if we do this, we won't charge you as much for electricity. So this is really a cost savings. And I'll end with, I think, the best quote pertaining to this industry. I mean, this has happened. There are so many terrible codes out there. And no matter how fast the hardware becomes, that code is not going to run any faster. With that, I'll end.